All right, we are talking about alkenes today. And so let's actually begin like we usually do in recalling the ways that we know how to make alkenes. And then we'll talk about what reactions alkenes can perform. If you remember, the alkene is the CC double bond. Alkenes. So how to make alkenes, this is a review. We're not going to learn any new ways to make alkenes. We already know all the ways we know. Okay, the most common way to make an alkene is using an E1 or an E2 reaction. So if we have some carbon attached to a leaving group, and remember our 5 good leaving groups, they're iodine, bromine, chlorine, water, and sulfonates. You can either do E1 or E2, and the product of that is an alkene. Now, as far as I know, there's only one other reaction we've seen that makes alkenes, and it's also a variation of the E1 reaction. It's the dehydration of alcohols. So if we have this alcohol and we treat it with H2SO4 in heat, this is called the dehydration of alcohols. And this reaction produces an alkene as well. Keep in mind that this reaction only works for secondary and tertiary alcohols. If you remember from yesterday's lecture, primary alcohols do the industrial ether synthesis, so they don't do this elimination reaction like the secondary and tertiary alcohols do. And there's just one last thing I think I'll mention, is that you can turn the alcohols into good leaving groups and then do the E1 and E2 reaction. I don't know why you'd want to do this, but you could do tosyl chloride and pyridine and convert the alcohol into a good leaving group and then do E1 or E2. I don't know why you would do that when you could just do H2SO4 in heat directly. I guess you might do this if you have a primary alcohol and you need to turn it into an alkene. You can use the tosyl chloride pyridine to turn that alcohol into a good leaving group, because you can't do the dehydration of alcohols with primary alcohols. Okay, so that is how to make alkenes. Okay, now let's see what reactions alkenes do. So what do alkenes do? So what reactions do? Great question. I'm glad you asked. So generally speaking, the alkenes do what are called not elimination reactions, addition reactions, the opposite of an elimination reaction. This is typical reactivity of an alkene. Addition reactions add stuff to the alkene. Okay. Let's take a look at a generic addition reaction. So if we have an alkene, say, that looks like this, cyclohexane with an alkene called cyclohexene, and you add some reagent, we'll talk about what those reagents are, and we'll call this reagent AB. An addition reaction would add the elements of A and B across the double bond. So one of the carbons of the double bond would get A, and the other carbon of the double bond would get B. So notice what the overall transformation in an addition reaction is. You lose a pi bond, but what do you gain? You gain 2 sigma bonds. And overall, this is usually energetically favorable. Sigma bonds are typically lower in energy than pi bonds, so to lose a pi bond and gain 2 sigma bonds, that's favorable. But what you may have noticed, if you're smart, well, even if you're not smart, you may have noticed this too, is that there is some things to consider when you add A and B. Certainly, I was not smart enough to think I would have to consider this. And the first consideration is, of course, stereochemistry. Because we're making new sp3 hybridized carbons, it's potential for A and B to be added as wedges or dashes. And particularly, we don't really care who's a wedge and who's a dash, but what we do care about is, will A and B be added to the same side, or will they be added to opposite sides? So for example, you could have a situation where A and B both get added as a wedge, or they both get added as a dash. Okay, and we call this syn addition. And we'll see that there are some reactions that proceed via syn addition where both A and B are added to the same side. Or you could have what's called anti-addition, where one of the A groups gets added as a dash, and then the other group, the B group, gets added as a wedge. And we call that anti-addition. So that's one thing we do need to consider is stereochemistry. We also have to consider something regiochemistry. And we saw this a little bit with the epoxide reactions where the nucleophile could add either to the left or the right. It's the same thing here with an addition reaction. And that's called regiochemistry, which region of the molecule reacts. And so if we ignore stereochemistry for a moment, we can either add so that A is on the top and B is on the bottom, or we can add so that B is on the top and A is on the bottom. So there's a lot of considerations for an addition reaction. Adding two things to an alkene is not a simple endeavor. You can add it syn, you can add it anti, you could add A on the top and B on the bottom, you could add B on the top and A on the bottom, or you could have mixtures of all of these possibilities. Well, it turns out that good news is most of the addition reactions we're going to learn are highly selective. They have a certain stereochemistry that they go by, and they have a certain regiochemistry that they go by. So we generally only get one product. Although the products are generally produced as mixtures of enantiomers, we'll worry about that later. Okay, so let's take a look at actually some of these reactions because this is all very abstract. But before we look at the first reaction, I want to mention one thing. It's the general reactivity of alkenes. So generally, alkenes are weak nucleophiles. And so because they're weak nucleophiles, they're going to react with strong electrophiles. That makes sense, right? If something's weakly nucleophilic, in order to get it to react, you're going to have to give it something very electrophilic. Otherwise, they're just not going to do anything. And that's what we see most of the time. Alkenes are pretty stable. We've seen that alkenes are stable even in the presence of super strong substances like Grignard and organometallic reagents. The alkenes aren't affected. So in order to affect the alkenes, we got to throw some really strong stuff at them. The key step in almost all the mechanisms of alkenes, we have an alkene and there's an electrophile that we add to the reaction, and the alkene attacks the electrophile. So you see a lot of this pi bond acting as the nucleophile and grabbing that electrophile. All right, let's take a look at reaction 1. Now, reaction 1 is called, well, it's got a pretty boring name, addition of HX. So addition of HX. It has another slightly more interesting name called hydrohalogenation. Which is a pretty interesting name. And the reason is that we're adding hydrogen and a halogen. And HX is equal to hydroiodic acid, hydrobromic acid, or hydrochloric acid. It doesn't work with hydrofluoric acid like many of the reactions in this class. Let's take a look at the mechanism of what happens. So we'll start with an alkene, a beautiful alkene, and then we'll add to it HBr. HBr is a pretty strong acid. It's a pretty strong electrophile. The alkene will grab the H of the HBr and kick out bromine as a leaving group. The result, well, let's actually go down here and show the mechanism down here. The result is that the alkene is now gone. One side of the alkene has got an H, and the other side of the alkene got nothing, and so it's left with just a carbocation. Okay, because we destroyed that double bond by protonating it with HBr. one of the carbons is going to get the short straw here. And then it turned out I chose randomly the carbon on the right. Got the short straw, I got the carbocation. But that's okay, because what else is present? Br minus. The Br minus is going to attack the carbocation, and then that's going to lead to the hydrohalogenation product, which is one of the carbons of the alkene gets a hydrogen, and the other carbon gets a bromine, or whatever halogen you choose. It depends on the acid you choose. Okay, so not a bad reaction. Adds the elements of hydrogen and a halogen across a double bond. Now let's talk about what's most important about this reaction. It's the regiochemistry. Okay, it turns out that the carbocation that forms is not random. So regiochemistry answers the question, which carbon gets what? If it's not random. It turns out that it's going to have to do with the carbocation stability again. So now let's take a look at a different alkene. Let's choose an alkene that is not symmetric like the other one. Okay, so this alkene has 2 methyl groups on the left and 2 hydrogens on the right, not shown. And let's go ahead and react this alkene with HI. And it turns out if we do this reaction, the major product is adding iodine to the more substituted side, the side with the most amount of carbons. And the hydrogen goes to the less substituted side, the side with the least number of carbons. The other possible product, which we don't see very much of in this reaction, is when the iodine gets added to the right and the hydrogen gets added to the left. So this would be the major product. Okay? And of course, then that means that this one's the minor. All right, so let's understand why. So to form the major product, what ends up happening is the carbocation forms at the more stable tertiary position on the left, putting the hydrogen on the right. Then when the I minus comes in, it attacks that more stable carbocation. Okay? So X, which is the halogen, goes on the more substituted side always. So X goes on the more substituted side because the reaction proceeds through carbocation. And we know that carbocation stability is a big thing. Let's compare. When the hydrogen gets added to the right, the carbocation is produced on the left. Versus if the hydrogen was added on the left, the carbocation would be produced on the right. And the left scenario is better because we have a tertiary carbocation versus a primary carbocation on the right. So that means the left option is better. The right option is terrible because primary carbocations are bad. And this has a name, a Russian name. It's called Markovnikov's rule. Okay, and what Markovnikov's rule, the way you can think about it is like this. The rich get richer. Which we know is true. And why do we call the rich get richer? Because, let me just scoot this over a second so I have more room to explain. Oops, I took my 3 with it. The rich get richer, and the reason we can think of it like that is that the carbon with the most hydrogens gets the new hydrogen. So the carbon with the most hydrogens gets another hydrogen. And the overall reason for this is because of the carbocation stability. So take a look at this case. We have this alkene right up here. Which side is going to get the hydrogen? The side that already has the most number of hydrogens. In this case, the right side has 2 hydrogens, not shown. So it's going to get the additional 3rd hydrogen, and that's indeed what happens. So if the right side of our alkene gets the hydrogen, that means the left side is going to get the halogen, the I. And so we call this Markovnikov's rule. It's a rule that explains the regiochemistry of some reactions. Okay, let's move on to the next page, and now that we've talked about the regiochemistry, we can talk about the stereoselectivity of this reaction. So stereoselectivity. And it turns out that there is none. Okay? Because we would just get a racemic mixture of enantiomers. Because carbocations are planar. Okay, let's take a look at an example here. So if we had, for example, this alkene, ethyl and phenyl on the left and 2 hydrogens on the right, and we treat it with HBr, we're going to add the bromine to the which side, left or right? That's right, we're going to add the bromine to the left side because that's Markovnikov's rule, where the hydrogen goes on the right side since the right side already has more hydrogens. And what we'll see here is that we're going to get a mixture of enantiomers. We can either get the product where the bromine adds from the top, or we can get the option, that would be R, or we get the option where bromine adds from the bottom, and you can convince yourself that this would be S. And so you can see the reason for that is that one of the intermediates in the reaction is the carbocation. So we could get, I'm trying to draw this sort of perspective view where we have a carbocation intermediate that looks like this, empty p orbital. And our nucleophile, Br, can either attack from the top or the bottom. And so that's why we get both enantiomers forming. There's no stereoselectivity, just like in an SN1 reaction. This is basically is an SN1-like reaction. The only difference is that instead of starting with the leaving group, we start with an alkene, and we generate the carbocation by protonating the alkene instead of the leaving group leaving. So it's very similar to an SN1 reaction in that sense. We are replacing an alkene with a nucleophile, and the way we do that is we add H to one side and the nucleophile, which is a halogen, to the other. And so, of course, because it goes through a carbocation, there's zero stereoselectivity. You get mixtures of top and bottom attack. All right, so that is the hydrohalogenation reaction. Congratulations, you've now learned the first reaction of alkenes. But we're not going to stop there. We've got about 10 reactions to get through, and I think we'll probably try and get through about 4 today. Yeah, let's do 4 today. Okay, so that leads us to reaction 2. Reaction 2 is addition of X2. This one has a fancy name called the dihydrohalogenation. And this one only works with Br2 and Cl2. Doesn't work with I2 for whatever reason. Okay, so let's take a look at the mechanism and the product that we get. Okay, and so we're going to start off with an alkene, and we're going to treat it with Br2. And the solvent is typically tetrachloromethane, carbon tetrachloride, CCl4. It's an inert solvent, doesn't really do anything. So the product is actually adding 2 bromines to the left and right. So we delete the alkene. Instead of adding H in Br, we just add Br in Br. Okay, not bad. Let's take a look at the mechanism. The mechanism's a little bit funky. Okay, so in the first step of the mechanism, the alkene is approached by the dibromine. So BR looks like this. and it's the elemental form of dibromine. What happens is the alkene gets close to the dibromine, and what do you think is surrounding these bromine atoms? Well, electrons, a lot of electrons. Bromine is covered with electrons. It's a pretty high on the periodic table, so it has a lot of electron shells and stuff around it. And what happens is, as the alkene approaches the dibromine, the electron cloud becomes distorted. So I'm going to kind of try and draw the electron cloud here. And the alkene has electrons of itself, so it's going to kind of repel electrons and push them towards the other side of the dibromine. We call this an induced dipole. Because induced dipole, not pile, induced dipole. And the reason is that as this electron cloud gets pushed, it creates a delta plus on the side that was approaching the alkene and a delta minus on the side far from the alkene. So this is called polarization, where we're polarizing the dibromine molecule. And so what this does is actually create a electrophilic bromine close to the alkene. Remember, the alkene is a nucleophile, a weak nucleophile, and it needs to react with an electrophile. But if you look at something like Br2, you might say, well, where's the electrophile there? There's no delta plus, there's no delta minus, they're equal polarity. But it turns out that there's a hidden delta plus, delta minus that's only revealed when the alkene gets close and causes an induced dipole. So what's going to happen is, and the mechanism here is really cool, the alkene attacks the delta positive bromine, but that bromine has lone pairs of itself, and it's going to attack right back onto that alkene. While this is all happening, the bromine-bromine bond breaks. So let's follow the product of our arrows and see what we actually make here. We make something called the bromonium ion. It looks kind of like an epoxide. It's a three-membered ring with bromine in it, positive charge on bromine, and this bromine's got two lone pairs on it. And this is called the bromonium intermediate. The way I think of this, and maybe this helps you, maybe it doesn't, so just you can think of it like this. Imagine the alkene starting to attack bromine on the left. That's going to start to generate a carbocation on the right. But this bromine is covered in lone pairs, and it's not going to let that happen. It's going to be like, I'm not going to let you have an empty octet carbon. I'll save you. As the carbocation forms, the lone pairs on this bromine fulfill the empty octet immediately before the carbocation has a chance to form. And the result is that we get this three-membered ring with bromine. This is really the molecule's way of avoiding a carbocation. This is the molecule's way of avoiding a carbocation. But it's still a reactive intermediate, and it looks kind of like the epoxide. And just like the epoxide, it's electrophilic at the carbons that are attached to the bromine. So what happens is the Br minus that was kicked out back here comes back and attacks the bromonium and then opens up the bromonium. Doesn't matter if it attacks the left or the right. In fact, we would never be able to know if it attacks the left or the right because the product's going to look the same. And then the net result is anti-addition of dibromine. Because of the bromonium, you get addition to the opposite side. So one bromine comes in from the bottom, the other one's left on the top. Now, in terms of regiochemistry, there is none because we're adding the same group to both sides. So it doesn't matter if bromine goes to the right or the left because it's bromine on both the right and left. So regiochemistry is not applicable because A equals B equals Br or Cl. Right? And remember that regiochemistry is whether A goes to the top or B goes to the top, but if A and B are the same, who cares? So let's see what this anti-addition looks like in terms of wedges and dashes. Because this reaction does have stereoselectivity. Because it doesn't go through a carbocation. It goes through this bromonium, which is not flat. So the stereoselectivity is we get anti-addition. Let's take a look. So if I took this alkene here, cyclohexene, and treat it with Br2 and CCl4, carbon tetrachloride is typically the solvent, we get anti-addition. So one of the bromines ends up on a wedge and the other ends up on a dash. So we call this anti or trans sometimes. But we're also going to produce the enantiomer. So we'll also have the possibility where we have Br as a dash on top and Br as a wedge on the bottom. So these two compounds are enantiomers. So let's take a look at the mechanism of how these enantiomers are forming. What happens in the first step, the bromonium forms. And so the bromonium looks like this. Okay, we can just show the bromonium as being wedge and a wedge. Obviously, you can't have a trans bromonium because it's impossible to have a three-membered ring that's trans. Both groups need to be bonding in the same direction towards the bromine. They can never reach otherwise. And then the other bromine, Br minus, is either going to attack from the bottom or the other bromine will attack the top side. And there's 50-50 chance of it attacking either the top or the bottom. So if it attacks in the left case scenario, then it's going to invert the bottom stereocenter in an SN2-like fashion, and that's going to lead to the first enantiomer. And if the bromine attacks the top, then it's going to invert the top stereocenter, leading that to become a dash in an SN2-like fashion, and that's going to lead to the top product, the right product. So because each of these possibilities can occur with equal probability, we get a 50-50 mixture of both enantiomers. Okay. So in other words, we only have control over the relative stereochemistry. Okay. We get a racemic mixture of the enantiomers, but of those enantiomers, they're both one wedge, one dash. So there is some degree of stereoselectivity here, and specifically, they're opposites. We don't know which one gets the wedge and which one gets the dash. All we know is that they're always going to be opposites for the dihydrohalogenation reaction. All right, let's take a look at reaction 3. Reaction 3 is actually a subset of reaction 2. It's a variation of reaction 2. Reaction 3. Reaction 3 is the addition of one halogen and one OH. An alcohol. We call this the Halohydrin reaction. Halohydrin formation. Let's take a look at this reaction. So we'll take an alkene, and we're again going to treat it with dibromine or dichlorine. This works with Br2 or Cl2, not I2 or F2. And the only difference actually between this reaction and the one right before it is instead of using CCl4 as the solvent, we're going to use H2O as the solvent, water. The product of the reaction is going to look like this. We're going to add a bromine, and we're going to make an alcohol. Now beware, this reaction is really important because we know a lot of reactions that involve alcohols, don't we? So this is another way of making an alcohol. So we need to be keeping mindfulness about this reaction, knowing that this can string back into our conversation about alcohols. You know, reactions in like PCC and Jones. This alcohol can enter those reactions. Let's take a look at the mechanism of the transformation. The first step is identical to reaction 2. The dibromine gets close to the alkene. One bromine attacks the alkene attacks back, and then one of the other bromine leaves. And that's going to produce for us the bromonium ion. Okay, and here's where the difference occurs. Instead of another bromine attacking the bromonium, we now are in water solvent. And so water can come in and act as the nucleophile. And the water is actually going to attack the more substituted side of the bromonium, similar to epoxide opening under acidic conditions. And that's going to lead us to almost the product. We just have a pesky proton still on our water. So then a generic base is going to come along, maybe another molecule of water, maybe the bromide from the beginning comes and takes away one of those pesky protons. You're welcome to use generic base for this. And then that's going to lead to the final product. Notice this reaction does have regioselectivity because we're not just adding the same group to both carbons. One carbon's getting a bromine, the other carbon's getting an alcohol. And so the regioselectivity in this reaction is that the OH ends up on the more substituted side. In other words, the OH group goes onto the carbon of the alkene that has fewer hydrogens or more other carbons. This reaction also has stereoselectivity, and it's anti. So let's take a look. We took this alkene here, and we treated it with Br2 and H2O. One of the bromines is going to be added as a wedge, and the alcohol group will get added as a dash. Or the opposite could also be true. We could end up with the bromine as a dash and the alcohol as a wedge. We don't know exactly who's going to be dashed and who's going to be wedged. All we know is that the product will be one wedge, one dash. So we call this trans or anti. Both terms are acceptable. And again, no control over the absolute stereochemistry. Only relative control. Meaning we get a mixture of both of these enantiomers. Okay, so that's reaction 3. All we do is change the solvent from reaction 2 from carbon tetrachloride to water, and suddenly we get a completely different product. Okay, and now it's time for reaction 4, the last reaction of today. We're flying through these. Reaction 4 is very similar to reaction 3. It's the addition of X and OR. And we call this the Haloether formation. So very similar to adding H2O with bromine. Instead, we use an alcohol as the solvent. So the way the reaction works is we take like Br2, and instead of H2O or CCl4 as the solvent, we'll use methanol as the solvent. The product is going to be an ether. The alcohol group will always attack the bromonium from the more substituted side, so we'll end up with the ether on the more substituted carbon. And the stereochemistry will be anti, as always. So the ether group will be opposite whatever the bromine is. So we'll get these two possible products. Okay, so the stereochemistry, just like all of these bromonium ones, is anti, and the regio is that OR, the ether, to more substituted carbon. Okay, that's a pretty sweet reaction. A nice way to make an ether. Let's take a look at the mechanism. Okay. The mechanism of these all start the same. The dibromine approaches the alkene and an induced dipole forms. The alkene attacks the bromine attacks back to form the three-membered bromonium. Okay, the bromonium can either form from the top or the bottom. So we can have the wedged Br plus, or the bromonium could attack from the bottom with 50-50 probability. So we get these two possible bromoniums. And then our methanol will attack the more substituted side, leading to an inversion at that stereocenter. Okay, so if the methanol attacks from the top, that's going to invert that stereocenter, causing the dashed methyl group to become a wedged methyl group, and our OMe group is going to be coming in on the dash. The bromine is going to stay a wedge. Okay. And then finally, the last step is a generic base will come along. Maybe it's another molecule of methanol. Maybe it's the bromide from the first step. It's going to go ahead and remove that pesky proton and lead to our final product. Okay, so this apparently led to this enantiomer over here. And this bromonium, you should draw out the mechanism and convince yourself that this is going to lead to the other enantiomer. Okay. So that explains the stereochemistry of why we're getting both enantiomers here. It's because the bromonium can form either on the top side of the alkene or the bottom side of the alkene with equal probability. It all just depends on how the bromine approaches the flat alkene. Just like a nucleophile can either attack the top or the bottom of a carbocation, the dibromine can either approach the top or bottom of this flat alkene. And depending on which face of the alkene it approaches, we can get both enantiomers of product. Okay. So the key thing to remember is that whatever the solvent is can really affect the outcome of this dihydrohalogenation reaction. In reaction 2, we used an inert non-participating solvent, carbon tetrachloride, CCl4. When we did that, we just got two bromines to the alkene. If we switch the solvent to water, we got bromine and OH to the alkene. In my opinion, this is the most important one because remember that the OH, we can do other reactions to the OH, like PCC or Jones, or we could depronate it, do the Williamson ether synthesis. Yeah, there's a lot of stuff we can do with alcohols. And then finally, reaction 4, if we change the solvent to an alcohol, then we add bromine and an ether across the alkene. So again, really changing up the outcome of the reaction, all based on the solvent that we use. So that's a subtle change, and so it's going to be critical for reactions 2, 3, and 4 that you make sure you indicate which solvent you want to use, because you get a completely different product depending on which one you choose. Okay, let's stop right there, and we will learn about the remaining reactions. I think there's about 10 of them for alkenes starting in the next lesson.